Can you guys hear me okay? Excellent. Hey, Mike, can you unlock your laptop for me? Is it working? All good? Yeah, looks good. Okay. Thanks, Mike. He's please thank my co-founder. All righty. Let's find my mouse. Bring this over. All right, let's get started. First, before I talk about myself and introduce, I'd like to know a little bit more about you. So I'm going to hold what I call a MIMO Myers-Briggs test here. So industry versus academia. Industry, hands. Academia. Okay. Software versus hardware. Software. Hardware. Wow. Okay. Startup versus enterprise. Startups. Enterprise. Okay. Wow. And extrovert versus introvert. Extroverts. Introverts. I'm surprised introverts raised hands. Thank you so much for that. Excellent. Well, let's get started. I'd probably introduce myself a bit. I'm here to talk about realizing engineering general intelligence. I think there's a lot of similar themes that happen today, and hopefully I can talk through my slides, give you a live demo. I'm crossing my fingers here on our test development servers, so hopefully it works. But I'm here to talk about what engineering general intelligence is, why we need to realize it, how do we do that? But let me start with first who we are. So we are a small startup founded in late 2023. Wojtek and I went to the gentleman in the middle. He's a professor here at CSAIL. He and I went to grad school here together about almost 30 years ago. Been old friends, and I was retired in 2022, bored and very anxious. He called me one day in 2023 and said, I wrote this paper called Large Language Models and Humans in Design and Manufacturing. You want to start a company? I'm like, hell yes. Like, I don't know what that is, but I'd love to do that. That paper was co-authored by Mike as well. So three of us started a company late 2023. We raised our Series Seed and Series A. We invited a whole bunch of my coworkers. My previous CEO hated me for it because I started stealing all the good people, of course. And we're just amazing team. I'm so proud to be working with. To date, we raised $31 million from top industrial AI VCs, many of whom have access to not just capital, but also to our potential customers. And we're tackling almost everything here. The definition of ICP should be very narrow and deep, but we're really trying. It could be very narrow, it could be very deep, but it'll make a lot more sense once I give you the live demo of what we're doing. Okay, so that's somewhat who we are. So let's talk a bit about what engineering general intelligence is. Okay, just want to make sure I have time here. So what is EGI? It's a domain and engineering specific AI stack that really bridges the gap between atoms and bits. We talk a lot about bits today, and the LLMs are really good at bits. How does it stack up on the atom side? Not so good. Mike just talked about world labs and a bunch of things that are really bridging these gaps as well, simply put. And we're really trying to also replace probabilities of generative AI and more of the neural nets out there that's non-deterministic with determinism. I think there are, I guess, pros and cons with both, but I think ultimately what you want to do is leverage both of them well. So we're focusing more on the more deterministic logic grounded in physics and manufacturing constraints, mainly because that's the market that we're going after. And that's also, I think in many ways, a blue ocean because it's really not solved. And we're claiming that we can solve it. We have a methodology to solve it. So let's at least compare what AGI is with AGI. In terms of logic, it's more probabilities. As you know, get a lot of content in, put it into this big neural net, see what comes out. There's pre-training, post-training. There's a bunch of stuff that you do with it. A lot of times it hallucinates. And oftentimes it's not necessarily good for engineering. For AGI, more bits to atoms, it's deterministic, it's repeatable, traceable, verifiable, version control. It sounds a little bit more like code. So I'll talk a bit more about that. Foundational model for AGI is a lot more of internet data, text and videos, as you know. AGI is a lot more based on physics, so we leverage physics as well. And if you leverage it well, you can have almost infinite amount of, synthetic data as well. There's a bunch of institutional knowledge. We work with our customers, and when we talk to them about certain things, you know that the output of the drawings or CAD, all these designs, there's something in their heads that's not expressed. And that bridging that gap and really trying to express that and try to contain it into our intelligent learning system, it's also a challenge. There's a bunch of data sets in enterprises, structured and unstructured data as well, and really trying to ingest all of that and make sense of it. That also is a big challenge here too. Outputs for AGI, more suggestions and conversations, and I think it's getting a lot more structured. But for AGI, what we want is manufacturing recipe. Give me something that's deterministic. Give me something that's a deterministic logic graph for constraints, and that helps me not only with manufacturing, but also with design, DFM. So we call it a DFM Copilot as well. Hopefully we'll jump into the demo, that makes sense. Okay, so now that you know everything about AGI, let's talk about why we need to realize this. So current stack does not quite work for engineering, as you know. Many of us spoke about that. By the way, give me 1 second. Many of us talked about that. And it's because a lot of times, big tech is investing a whole bunch of money. And yet it still fails at bits to atoms. Just to give you an example, here's a manual human input. It's a language that 5-year-old can understand. These are the parts to this widget, and this is how it kind of put together. And these are the number of the parts that you can get through some other table that you see. Tried hard to get the LLM to work, and just out of the box, it doesn't work. And in many ways, engineers will lose trust very quickly if this keeps on happening. I'm sure many of you might have experienced this already as well. So there are certain things that agents are really good at, certain things that they're not yet, and we're tackling the not yet piece. If you look at it in the market side of things, it's a big market, big problem. So annual global output of manufacturing is 40 trillion, 47 for 2025. It's estimated about half of it goes to waste of one form or another, and about 20 cents on the dollar is just mainly due to inefficiencies. So there's a lot of opportunity here for innovative companies, big and small, to be able to address these inefficiencies. Right out of the gate, it'll be almost $8+ trillion market, and there will be a lot less waste. It's not just about the bottom lines, but also the top lines as well, or the other way around. So important to realize this and making sure it's not just non-deterministic tool that we have, but fairly deterministic tools that we can leverage for engineering. So how do we do this? Okay. This is a bit more of a sort of markety slide, but we invented a novel AI stack that's distinct domain specific, precise, and traceable. And basically, we're writing code for engineering. What does that mean? So for many long time ago, in a galaxy far, far away, engineering and programming were two separate worlds. And through AGI, we're putting this together. So what we're saying here is that anything that happens in engineering, you can describe it as a programming language, and vice versa. You can program language, whatever happens in engineering. Of course, there's constraints and physics and all of that involved, but putting just these two together opens up a whole bunch of other use cases. And that was a big part of Wojtek and Mike's and a bunch of other people's research work, applying large language models, what's really necessary out of that. So EGI can even do a lot more different use cases for both design and manufacturing, from CAD, understanding design explorations, simulations, many of the things that Mike showed before, all the way to manufacturing. You can do process planning, factory integration, line balancing, and a bunch more things. And we claim that EGI can solve all of this. And that bridges the gap of LLM that's lacking today. Okay, so how much time do I have? 9 minutes. Okay. Oh, okay, there it is, 9 minutes. Let's go into the demos. Hopefully it works. Couple demos I'm going to show. So what we did was, from a platform, we built a couple of use cases. We built actually a lot of different use cases, but the two I'm going to show is a lot more applicable for our customers. So one is process planning. You ingest a 3D model. You can ingest also bill of materials, a bunch of other stuff. And what it'll output is a sequence, work instruction on how to put this thing together. And the second demo I'll show you is on the more the technical drawing. Given a 3D input of some part, then it will give you GD&T, and you can talk to it, etc. Okay, let's jump into demos. Crossing my fingers here. So I just have a few that are already kind of pre-prepared, so I don't have to wait around for it to process. So first thing that we do is we ingest the 3D model. Here is an engine that Mike here created, by the way, and you can see that. Let me give you, there's a fixture there that we excluded for now, but it basically took a 3D model, just the geometry, and a bunch of other metadata, and then used machine learning to try to correlate the two. At which point, then you stop and say, hey, human, did I do it correctly or not? And whatever the human inputs and edits, that's fed back in to reinforce our training afterwards. So once this is done, it took about 5 minutes to get this one going. Let me reset and show you. So then this is kind of happening live here. So we're putting together all the pieces and using physics, basically, F equals MA, and a bunch of other software techniques. We figured out what goes in and what the sequence should be. There's certainly human in the loop for some of the parts that are deadlocked or interlocked, or if the 3D model has errors or it's not watertight. There's a bunch of stuff that we have to soften up the logic for it as well. But it works. And we've done this for a few of our customers who are thinking about, here's the next model of X that they need to sell in the next 2 years. The model's done, how to prepare the manufacturing. There's bill of process that we do, and then we also do constraints around the plant-specific bill of process and work instructions as well. The other cool thing here is that, let me pause this for a sec. So again, the input here is just 3D model and bill of materials, and we mainly leverage physics. There's a sequence of historical data that all of these manufacturers have, and it's a variation of the existing theme that they do. So what we can do is ingest the sequences and apply it, and also be able to validate that through physics as well. There's so much to talk about, but anyway, the other thing here is that we can have multiple sequences. So it's not just one way to put this together. There's multiple ways to put it together. And a lot of times the engineers go, like, we kind of evolved into this, but is it really the most optimal? They don't know. So what we do here is we create an assembly graph, cost function at each pairs of parts being put together, and we can create an optimization like this and give you multiple sequences how to put this together. And that, it was software-wise, it's pretty simple. And a lot of our customers were just so blown away by this that I wanted to show it to you here. So you can see the diffs, and the way, as a software guy, looking at this is very different from the hardware guys looking at this. They're like, oh my gosh, why couldn't we? That would have made sense. This sequence would have made sense. Very, very cool stuff here. If I can say that. All right, so that was sequence planning and process planning as well. let me go into the next demo, is tech drawing. So let me see, I have about 5 minutes left. I'm going to blaze through this, and then maybe I can take some questions. Definitely want to talk to you more. If I can talk to everyone here, I would. So the input into this second demo is just the geometry. That's all it is. And so what we do first, again, is we ingest it, understand a bunch of pieces of the geometry, and it automatically labeled these things from datums to the bends and clearance hole, et cetera. And you can say, OK, that looks good. And the user actually can go and fix things if they want to. Then let me fast forward. It took about a minute to process this. Oh, by the way, the sequence, it took about 5 minutes. I think I mentioned that. So then we go into this piece right here after about a minute of processing. Let me put this away. And I'm going to type in some prompts. Well, let me actually just show you this first. So this is all the PMI data that it figured out just from geometry. And we can say, well, it's too much info. Give me some of the views. So there's view 1, view 2, view 3, et cetera. And it tells you the linear dimensions as well as the tolerances and control frames, et cetera. It can also do this in 2D as well. And we can export it out to Siemens, whatever platform that you want. And it looks exactly like a human did it because we actually have a full script and a sequence of how this is all put together. So there's the simple output, but sometimes it's wrong. So we also enable the humans to edit things. They can also move things around if they want to, like that, and beautify it, and all of that gets fed back into the learning system. Okay, so then you can prompt some stuff. So I have some, I prepared some. Tell me about this part. Hopefully no one's using the dev. Okay, so it's basically saying the sheet metal part with several bends, holes, and cutouts, key features, datum ABC, blah, blah, blah. Okay, and then geometric tolerances, dimensions, et cetera. Cool. Okay, so I can say how many holes are there? So there are 8 holes. Ooh, okay, I did not know that. And I can say, well, show me the view with holes. So whatever you prompt, it's not only about isolated interaction, but it understands what's going on the 3D side. So it's showing me a view with, I can see 4 holes. Show me the other view with holes. So you can interact in both circumstances here. You can see there are smaller holes over here with a smaller radius. And I can just kind of move this around and show you that. Let me select this guy. Okay. So then I can do stuff like, change the tolerances and it'll update it. What I want to at least quickly show you here is maybe our secret sauce is this piece. So what you see here is the code that I was talking about. It basically, from the input, it wrote, let's scroll down, about 1,900 lines of code that describes exactly what's going on over here. And you can actually talk to it. And the grammar in and of itself is vast. And that's where you can get the access and modifications and chats and interactions with digital objects that are physically constrained, but also in a natural language, but very succinct and very precise. And all of that code, again, you can keep it in version controls, you can syntax check it, you can physics check it, et cetera. Yeah, I mean, there's a bunch of other stuff I can do, but I want to make sure I'm running out of time, so hopefully I can take a question. I saw sorry, I saw someone back there. Okay, go ahead, please.
But So does your AI also say no?
So yes. So it basically I get two different examples because one we're leveraging a lot for physics. This one less so, but it's more about historical data, et cetera, and the structure of the code that we create. When we're using, let's say, the sequence planning, it's useful for cold starts. So a lot of times when we talk to a large enterprise, they're like, we're not going to give you any of our data because you're a tiny company. Like, what do we know? So just give us this. We'll show you, and we use it as a cold start to show the sequences, and it works. So, and then on that demo, what we can also do here is be able to drag and drop. You can see the sequences. You can just drag and drop, and every time that happens, we can say rerun the physics simulation and see if it works or not. So I think that was your question. Okay.
All right. Thank you so much, Bob, for sharing your insights.
Thank you.